What's up, everybody, and welcome back to OpenStax Algebra and Trigonometry, Chapter 3, Section 1, Functions and Function Notation. Let's do it. So the first question is, what is the difference between a relation and a function? So a relation is essentially any set of ordered pairs, like we think of an x and y value. So for example, we could have 3, 7, 4, 2. That's a set of ordered pairs with x and y values like so. So this is always going to be a relation. This is also a function in this case, and what distinguishes this from just being a relation, what makes it also a function, is because every x value just goes to one y value. So for example, if I were to add one more xy pair, if I was going to add 3 to 9, this would no longer be a function. It would still be a relation, but it would no longer be a function, because again, a function is a subcategory of a relation. So we want predictability when we're talking about functions. We want to know that if I have 3 for my x value, we have a definitive 7, not, oh, 3 could be 7 or 9. So that's the difference. Boom, done. Why does the vertical line test tell us whether the graph or relation represents a function? So if we go back to the idea we just discussed in number 1, we want every x value going to a y value that we can predict. So we don't want to have, for example, an x value of 2 go to either 10 or 12. So let me show you an example. So let's say we have this function as our graph. Now the vertical line test basically says if we draw a vertical line straight down through the function and we hit more than one point, it fails, meaning it's not a function. Well, this makes sense because, again, as I mentioned in question 1, we want every x value to give its own y value, right? So in this case, you can see the x value is a vertical line. Let's pretend this is like an x value of 3. This would be maybe an x value of 3 comma 7. I'm just kind of making this up, but you get the idea. This would be a 3 comma, let's say, negative 4. So what we have is the x value 3 giving us two different y outputs. We get a 7, and down here we get a negative 4. So this means it's not a function, and you can see that when we have a graph of a function, we can quickly verify with this vertical line test. Conversely, if I had a function kind of going like this, okay, we see that this is okay for the vertical line test. I can pass a line straight through at any point on the function. I'm only going to hit one point. So that's how you do it. Done. Why does the horizontal line test tell us whether a graph of function is 1-to-1? So 1-to-1 means also not only do we have, this is a function, right, where each x is giving its own, one output. Now we're saying that we want the same relationship back, meaning, for example, if I look at a quick graph of a parabola, this is not 1-to-1, right? But it is a function because every x value gives a definitive y value, but we don't have it going the other way. So for example, we can have a value here. I'm just making this up. Let's say this is 4 comma 2. So that's a y value of 2. And then we also have over here negative 4 comma 2. So this would no longer be a 1-to-1 function because we have a repeat of y values. This can be easily demonstrated by the horizontal line test, right? If we draw a horizontal line through a function and it hits it more than once, it's failing this horizontal line test, meaning it's not a 1-to-1 function. So the main way to determine if this is a function is to see if we have a repeat of x's. For example, if we have the same x value, aka like a here, if we had another one going to a different value, then it would not be a function. But we don't have that. All the x values are unique, and even though we have a repeat of y values, it's all good. It's still a function. It's not 1-to-1, but it's still a function. Boom, done. This is a parabola, and a parabola looks like this, and this is, of course, a function. Again, we don't have anything where it's going to fail the vertical line test, so this is a function. Boom, done. This is also a parabola if you were to graph it. And by the way that you're going to, a big tip off that this is not going to be a function is if that y value is squared, but it's not. The x value is squared, that's all good. So this will be a function as well. This is again a quadratic, meaning a parabola. Now it happens to be facing down because it's got a negative a term, but parabolas are good to go. They're functions. So this is a function. Done. So this one is definitely going to be a function as well because there's no way we can get two different y values for the same x value. But I'm going to show you what the graph looks like as well. So you can see with this graph, yes, there is an asymptote right here, but that doesn't matter. The fact is, at every point, it passes the vertical line test. So this is a function. Done. This is definitely going to be a function because we can see that, first of all, there's no exponent to the y. That's going to be a big indication that it's not going to be a function. It's not squared. It's not to the fourth. So this is definitely going to be a function, but I want to show you what this graph looks like as well. So here we can see at every point it's passing that vertical line test. So this is definitely a function. Done. This is also going to be a function. Again, one of the biggest telltales that it's not going to be a function is if we have an exponent on the y, but we don't. So this is pretty much good to go, but I do want to show you what the function looks like. So once again, applying the vertical line test, we see that it hits the function only once at every point that we can think of. So it is indeed a function. Done. Y equals x cubed is definitely a function. Again, you can have as many exponents as you want. On the x, it's still going to be this nice function relationship. This is a standard function, and in case you want to see what it looks like, it kind of looks like this. Boom. And of course, this passes the vertical line test at every point, which means this is, of course, a function. Done. So this one looks a little funny with that plus or minus, but really what this is this is a regular quadratic, meaning a x squared function in disguise. So this is actually a parabola. And you can also kind of tell, hey, it's not like I'm going to get a single x value that's going to give me two different y outputs. The other way around, maybe, yes, but not in a way to disqualify it from being a function. So now I'm going to show you what the graph looks like. So of course, you can see this is simply a parabola. The left side is the minus side. The right side is the positive side. Passes the vertical line test. It is a function, and done. So this one is definitely not a function. As I mentioned in previous problems, when we see that y squared, that's our telltale sign that this is probably not a function. Also, I can pretty quickly show an example for like check this out. If I put in 1, right, I'm going to get 1 for y. But also, if I put in 1, I could also theoretically get -1 for y because -1 squared is still 1. So that means I have an x value going to one value and then an x value going to a different y value. That disqualifies it from being a function. Now, just to show you what the graph of this looks like, it's a big X, so you can see it fails the vertical line test. I'm hitting 2 points, 2 points, 2 points, 2 points. So this is not a function. Done. So here we're meant to evaluate all of these functions and plug in. So when they say f of -3, it means I'm plugging in -3 for x. So for this one, I'm plugging -3 in for x. That's 2 times -3 is -6 minus 5 equals -11. For this one, I'm plugging 2 in. 2 times 2 is 4 minus 5 equals -1. For -a, I simply replace the x with -a, and it equals -2a minus 5. For this one, I plug a in, but then I negate the entire function. So it's 2a minus 5, but the whole thing is negated, which then means we distribute that negative. We get -2a plus 5. And last but not least, we're doing a plus h. So I replace the x with a plus h minus 5, and then I can distribute, and I get 2a plus 2h minus 5. So these are all your answers. Done. So for these, we are replacing the x value with whatever we have in the parentheses. So f of -3 becomes 2 minus -3 plus 5. That, of course, a minus a negative becomes a plus. So we get 2 plus 3 is 5, square root of 5 plus 5. Now we plug in 2. So we have square root of 2 minus 2 plus 5. 2 minus 2 is, of course, 0. So this just equals 5. So here we're going to replace that x with -a. So we have 2 minus -a plus 5. Minus a negative becomes a plus. So we have 2 plus a, radical of that, plus 5. Over here we plug in a, and then we negate the entire function. So we've got 2 minus a plus 5, but then we multiply this entire thing by -1, which gives us -√2 minus a minus 5, right? That negative hits the 5 as well. Last but not least, we plug in a plus h, and so we've got 2 minus that entire binomial, a plus h, plus 5. And now we'll distribute that negative to simplify a little further. So we got 2 minus a minus h, and then we got the plus 5 out here. Boom, done. So here we're going to replace the x's with -3. So absolute value of -3 minus 1 minus absolute value of -3 plus 1. And of course, -3 minus 1 is -4. -3 plus 1 is -2. Absolute value is the positive purifier. So absolute value of -4 is 4. Absolute value of -2 is 2. And we're minusing the 2, and that gives us 2, right? That minus just stays there. Now we're going to plug in 2. So we got 2 minus 1, absolute value, minus 2 plus 1, again, absolute value. So 2 minus 1 is 1. 2 plus 1 is 3. Absolute value of 1 is 1 minus absolute value of 3, which is 3. 1 minus 3 is -2. Now we plug in negative a. So this is just a matter of replacement. So we're replacing x with minus a like so, and then here we're doing the same thing. And really there's nothing else we can do. We're just plugging it in, we're replacing it. We don't flip this to a or anything like that because a itself might be negative, so you leave it like this. Now we do the same thing. This is plugging in positive a, so we're just going to replace everything with positive a, but then we're negating the entire thing. So we're basically distributing a negative to the whole thing. So watch this, see if we've got room here. So we got negative absolute value of a minus 1, and then that minus is going to turn into a plus, plus absolute value of a plus 1. Last but not least, we got a plus h, so we're just going to replace the x with a plus h minus 1 minus absolute value a. X is going to replace with a plus h plus 1. Boom, done. Given the function g of x, evaluate g of x minus g of a over x minus a. This you can mostly ignore. This is just preventing the case where x is equal to a and we divide by 0. So check this out. G of x is simply x squared plus 2x. G of a, which we're subtracting, is simply replacing the x with a. So we got a squared plus 2a over x minus a. So let's see if we can simplify by distributing the negative. So we got x squared plus 2x minus a squared minus 2a all over x minus a. Now I'm going to rearrange this on top a little bit so we can do some factoring. So this is now pretty cool because I can factor this as x minus a and x plus a. And this one I can factor out a 2 and gives us x minus a. And this is great because I got an x minus a in both of these, here and here. So I can further simplify this. I can pull that x minus a out like so. And then I've got in the x plus a and the plus 2. So it kind of combines like that. And this is now all over x minus a. Well, guess what? Now I can cancel. And my final answer is x plus a plus 2, done. Given this function, first evaluate f of -2. Again, that's going to entail simply replacing my x value with -2. So check this out. -3 times -2, that's 6. And that becomes a plus, of course. 8 plus 6 is 14. Now we're solving for f of x equal to -1. So we're trying to find the x value that gives us -1. So we'd say -1 equals 8 minus 3x. We're going to subtract 8 from both sides. We got -9 equals -3x. Divide by -3. Whoops. Divide by -3. And we get x equals 3 for part B. Done. Given the function f of x equals x squared minus 3x, evaluate f of 5. So for part A, we're plugging in 5 for x. So we're going to rewrite it like so. 5 squared is, of course, 25. Minus 3 times 5, which is 15. So the answer is 10. Done. Now let's do part B. Here we want the actual function value to equal 4. So we set 4 equal to x squared minus 3x. And here we're solving for x. So what we're going to do is we're going to set everything equal to 0 because this is a quadratic. So we got x squared minus 3x minus 4. Now we're going to factor like so, and we have x and x. What multiplies to -4 and adds to -3? That would be +1 and -4. So my two solutions now are whatever zero out the x here. So my two solutions now are whatever are going to zero out each of these binomials. So for example, here x would equal -1, right? -1 plus 1 is 0. And here, x would equal 4. These are my solutions. Done. Consider the relationship 3r plus 2t equals 18. Write the relationship as a function r equals f of t. So basically what they're saying in part A is we simply need to isolate r. So first I would subtract 2t from both sides. So we got 3r equals -2t plus 18. Then we're going to divide everything by 3. So now instead of writing r, we say a function of t is equal to -2/3 t, and then 18 over 3 reduces to 6. And there's your function. For part B, now they want to take that function and plug -3 in for t. So let's get f of -3. So f of -3 equals -2/3 times -3 plus 6. -2/3 of -3 is +2. 2 plus 6 is 8. Done. And now we solve for f of t when f of t equals 2. So we're going to solve for actually t, excuse me. So we're going to go up here. We don't have a ton of room. So we got 2 equals -2/3 t plus 6. Notice this is a linear equation, right? There's no exponent. So I'm going to isolate t. First, I'm going to subtract 6 from both sides. Boom. We've got -4 equals -2/3 t. Now I'm going to multiply by the reciprocal of -2/3, which is -3/2. Again, we're just trying to isolate that t value. So these cancel out, right? Reciprocal, or fraction times its reciprocal is 1. So that's what we want. And then t equals -3/2 times -4. So you can think about it like this. It's 3 times 4, which is 12, then divided by 2. So we got +6 because the negatives cancel out. Done. So in this question, we're using the vertical line test to determine if this is a function. And the vertical line test simply means we're drawing vertical lines and making sure we don't hit the function in more than one place with a vertical line. But if we do, it means it's not a function. And here, this vertical line is going to hit it here and here, which means this is not a function, and done. For 43, we're using the vertical line test to see if this is a function. And what you can see is everywhere that we draw a vertical line, we're only hitting this relation, this graph, one time, which means that this is a function, and done. Here we're using the vertical line test to see if it's a function. As you can see, everywhere we draw a vertical line, it only hits this relation once, meaning this graph does indeed represent a function, and done. For 47, we're using the vertical line test to see if this graph indeed is a function. And as you can see, everywhere I draw a vertical line, we're only hitting this graph once, meaning it is indeed a function. Done. Using the vertical line test, we can see that everywhere we draw a vertical line, we're only hitting the graph once, meaning this does indeed represent a function. Done. Using the vertical line test, we see that we hit this only once everywhere we draw a vertical line, meaning that this graph indeed represents a function. Done. Given the following graph, evaluate f of 0, meaning find the function value when x equals 0. So x equals 0 right here on the y-axis, and the function value is 1. That's the y value. So function value here is 1. And then solve for f of x equals -3. So what we're trying to do now is we're trying to figure out what is the x value when the function value is -3. And you see it hits -3 in two different spots. So the x value when f of x is -3 is either -2 or +2. Done. For 55, it says determine if the given graph is a one-to-one function. Well, this actually fails the vertical line test, meaning, if I administer it, I hit it multiple times, more than once, when I draw a vertical line through this graph, which means that it's not a function, therefore it can't be a one-to-one function. So not a function, and done. For number 57, as we administer the vertical line test, we see that every point through the graph, I'm only hitting it once, which means this is a function. And now the question is it one-to-one? So one-to-one, we administer something called the horizontal line test. So we can see as we draw horizontal lines across, we're also only hitting the function one time. So because of these two tests being passed, it is a function and it is also one-to-one. Boom, done. So for this one, first we administer the vertical line test to see that it is indeed a function because we're only hitting it one time with every vertical line. So we will say that this is a function. Next, to see if it's one-to-one, we administer the horizontal line test. And I can see with this line in particular, I'm hitting the function twice, which means this is not 1-to-1. Boom, done. So here we're given a relation, and the question is it a function? What you want to do when you're presented coordinates like this is you want to see if there's any repetitions of x. If there is, it is not a function. If there's no repetitions of x, meaning every x is unique, then it is a function. So here we have a 3, a 4, and a 5. So those are all different, and that's all good. So this would be a function. Just to give you a counterexample, what would make this not be a function is if then I had another coordinate that was 3, 7. So we're having a repetition of the x's, it would not be a function. The way to think about that is now I have 3 going to 2 different outputs. For this relation, 3 could give me 4 or 7, and that's not a predictable system, and that's not what we want for a function. But anyways, this does not have this point, meaning this is a function. Boom, done. Again, to see if this is a function, we're looking for repetitions of x. So I'm seeing a 5, a 10, and a 15. Those are all unique, which means that this indeed represents a function. Done. To determine if this is a function, I'm seeing if there's any repetitions of x once again, and check it out. I see a 10 and a 10 occurring 2 times and going to different values. So I've got 10 going to 8, but also 10 going to 14. This means it's not a function. And again, the way that I like to put it is we can see that this is not a reliable outcome. So for example, if I plug in 5, I know I'm going to get 3. But if I plug in 10, I don't know if I'm going to get 8 or 14 because they're both outcomes for 10. That's what invalidates it as a function. So this is not a function. Done. For this question, we're asked to solve for when f of x equals 1, meaning what is the x value when the function equals 1. So here's where the function equals 1. The corresponding x value is 2. So the answer is 2 for x. Done. For the following exercises, evaluate function f of the values f of -2, -1, 0, 1, and 2. So what we're doing is we're basically just plugging these values in for x and evaluating. So for example, f of -2 is 8 minus 3 times -2. -3 times -2 is 6, so it's 8 plus 6, which equals 14. For f of -1, it's 8 minus 3 times -1. That -3, remember I'm saying -3 because that minus sticks to the 3. So -3 times -1 is positive 3, and then it's plus 8 plus 3 is 11. For f of 0, we're just going to zero out this value, right? 3 times 0 is 0, so therefore it is simply 8. For f of 1, I'm replacing the x with 1. 3 times 1 is, of course, 3. 8 minus 3 is 5. And last but not least, f of 2, we've got 8 minus 3 times 2. Again, that becomes 6. 8 minus 6 is 2. Boom, done. For this one, we're trying to find f of -2. So I'm going to replace my x with -2 plus 3. So -2 plus 3 is 1. Square root of 1 is 1. So we've got 3 plus 1, which is 4. F of -1, we're going to do the same thing. Replace that x with -1. -1 plus 3 is 2. And we get 3 plus the square root of 2. To get a decimal approximation, we're going to plug it into the calculator. 3 plus square root of 2 is 4.414. So we'll say 4.414, done. F of 0, we got 3 plus square root of x plus 3. That's 0 plus 3, which is 3. And if we want a decimal approximation, we'll use the calculator. So 3 plus square root of 3 is 4.732. And there you go. Now f of 1, we got 3 plus, I'm going to plug it in here. We've got 1 plus 3. So that's, of course, 4. So square root of 4 is 2. So this gives us 3 plus 2, which is 5. Last but not least, we got f of 2. So we got 3 plus the square root of 2 plus 3, which is 3 plus the square root of 5. And to get the decimal approximation, we plug it into the calculator and we get 5.236. And there's the answer. Boom, done. So here with our function, we've got f of -2, that's 3 to the -2, which with a positive exponent, I write that as 1 over 3 squared, which is 1/9. For f of -1, we're going to replace it again, 3 to the -1, which I can just simply drop that negative exponent to the denominator, 1 over 3 to the first, or 1/3. For f of 0, it's 3 to the 0th. Anything to the 0th power is simply 1. For f of 1, that's 3 to the first power. That's just 3. Last but not least, we got 3 to the second power, which is 9. The following exercises evaluate the expressions given functions f, g, and h. So we got f of 7/3. So first of all, let's take this f function, which is 3x minus 2. And when they say f of 7/3, I replace the x with 7/3. And then we want minus h of negative 2. So what's the h function? We're going to put this in parentheses because we're subtracting that whole thing. So h is negative 2x squared. That's negative 2 squared, right? And then we got plus 3 times x, which again, I'm replacing all my x's with that negative 2. Last but not least, we got minus 1 like so. Now we'll go from left to right, though we're also going to hit these parentheses first, order of operation. So negative 2 squared is 4. And then we have negative 2 times negative 4, which is negative 8, plus 3 times negative 2, which is negative 6, minus 1. So we got negative 8 plus negative 6, that's negative 14, minus 1 is negative 15. So now I got 3 times 7/3, the 3's cancel out, and that's just a 7 minus 2. But again, there's a negative out here, right? So this double negative, minus negative 15, turns into a plus. So now we have 7 minus 2, which is 5, plus 15, which gives us a final answer of 20. Done. For this problem, we're meant to graph y equals x squared on this domain from negative 10 to 10 inclusive. So we're going to use Desmos to do that. So here we've got y equals x squared from negative 10, which is right here, all the way up to 10. So what you're seeing is if we want the range, the lowest point up and down is going to be here at 0, 0, or 0. And the highest point is going to be here at 100, and it's going to be at 100 either side. This means that the range is from 0 to 100 inclusive. Done. For the following exercises, graph y equals x cubed and the given domain, determine the corresponding range. So we're going to do this again in Desmos, y equals x cubed in this domain. So what I've done here is I've kind of really zoomed in. You can see the scaling. Actually, I can scale it even more. So now we can get a really nice view, and they want the range from this point, negative 0.1 to 0.1. And you can see that the corresponding y values are 0.001 approximately and negative 0.001, which means the range is negative 0.001 to 0.001 inclusive. Done. Here, once again, graphing y equals x cubed, but on this domain, so let's take a look in Desmos. Okay, so I've sort of adjusted the scaling, so now we can go back to negative 100 right here and up to positive 100. So that range you can see is now about a negative million to a million. So you just have to be able to adjust the window accordingly to see that clearly. So we have a range of negative 1 million, 6 zeros, positive 1 million, inclusive. Done. Here we're graphing y equals the square root of x on this domain, and we're trying to find the range. Let's check out Desmos. So now we can see a pretty nice clear picture. It's going from 0, 0 at the low point to all the way up to 100. It's going to a high value or max value of 10. So we can identify the range as follows. It goes from 0 to 10 inclusive. Done. Now we're talking about the cube root of x to give the range for this given domain. Let's go to Desmos. So here we've got a nice zoomed in thing. And by the way, I wrote here x to the 1/3. That's the same as the cubic root of x. So at negative 0.001, we're down here at negative 0.1 approximately, if I can get it right on the dot here. Boom, negative 0.1, all the way up to positive 0.1. See, just nudge it over just a touch, but you can see it's going to be 0.1, excuse me. So we got a range of negative 0.1 to 0.1 inclusive. Done. This one, we've got the same function as 85. We got the cube root of x from this domain. Let's check out Desmos. So again, now we've gotten a really nice window here, and at negative 1 million, it looks like it's negative 100. And then at positive 1 million, it's at positive 100. So the range is from negative 100 to 100. So our range will be negative 100 inclusive 100. These should be square brackets. Sorry, it looks a little curved. There's the final answer. Done. The number of cubic yards of dirt D needed to cover a garden with area square feet is given by this function. A garden with an area of 5,000 feet squared requires 50 yards cubed of dirt. Express this information in terms of the function g. So we would say that d is the number of cubic yards, and that's 50, equals g of a. So that means we take g with the area of 5,000. So this is the final answer. Done. For part B, it says explain the meaning of the statement g of 100 equals 1. So again, what we're putting into the function, the input is the area. So it's saying then, and then over here, that 50 is, this is the volume of dirt we need. So this is saying if you have a garden or something with an area of 100 feet squared, you'd need a volume of 1 cubic yard of dirt and to fill it up. So that's it. Let h of t be the height above ground in feet of a rocket t seconds after launching. Explain the meaning of each statement. So again, what's going into that input function, or into that function as an input, is 1, and 1 is t seconds after launching. So this, for part A, is saying 1 second after launch, and then this is the height. The rocket has a height of 200 feet. For part B, it's saying 2 seconds after launch. It's going to have a height of 350 feet in the air. That's how you do it. Done. I hope you enjoyed this video, and if you did, please click that like button. If you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.